Today, we're going to tackle a question that honestly sounds like it's been ripped straight out of a spy movie, but its roots are actually deep in the physics of our wireless world. We're going to explore what 5G is really capable of. And I'm talking about things that go way beyond just faster downloads on your phone. We're asking a pretty simple question that has a very, very complex answer. So, let's get right into it.
Okay, let's just put the main question right out there, because it's probably why you're here. Can a wireless network, think of 5G cell tower, actually detect your physical body, your presence, even if you've left your phone at home? No watch, no earbuds, no device on you whatsoever. It's a really unsettling thought, right? It kind of challenges everything we assume about being anonymous in a world that's so connected. And that's the exact mystery we're going to unravel.
So, the short answer is, well, it's complicated. And listen, if you take away only one thing from this whole explainer, let it be this. We have got to separate what is theoretically possible in a controlled lab from what is actually deployed out there in the real world today. The gap between those two things is huge, and that's where the real story is.
To really get to the bottom of this, here's our game plan. First, we'll look at why this whole sci-fi idea isn't even new. Then we'll dive into the actual physics of how radio waves can see. After that, we'll explore what makes 5G so different before we hit a really critical reality check, possible versus deployed. And then, finally, and this is super important, we'll look at where the real risk is, which might not be what you think, and we'll peek into the future with 6G.
Okay, first up, a science fiction question. Let's dig into the reality behind all the hype. So the first thing you have to understand is that this whole idea was not born with 5G. Not at all. For years, researchers in university labs have been showing that you can use the boring old radio signals from your Wi-Fi router or your Bluetooth speaker for something called RF sensing. I mean, picture a lab with a Wi-Fi router on one side of the room and a receiver on the other. That's it. And by analyzing tiny changes in that signal, they've proven they can tell when a person walks into the room, they can track their movement, and even spot gestures like someone waving their hand, all without a single camera and with that person carrying absolutely nothing. They can even see movement behind solid walls just by being clever about how they interpret those everyday signals. So how on earth does that work? Well, that brings us right to our next section, the physics of seeing. Now that we know it's been done with Wi-Fi, let's get into the basic science of how a simple radio signal can reveal so much about the world around it.
So what are we talking about here? The official name for this is RF sensing. Now, the big difference between this and, say, traditional radar is that RF sensing is usually passive. See, a radar system has to actively scream a powerful pulse of radio energy out and then listen for the echo. RF sensing, in this case, is much quieter. It just uses the signals that are already filling the air around us. The Wi-Fi, the cell signals. It doesn't need to shout. It just has to listen very carefully to how those existing signals bounce and bend and break as they move through a room.
Okay, take a look at this. This visualizes the whole principle perfectly. A radio signal, it doesn't just travel in one straight line from a tower to your phone. No, it bounces off of everything: walls, the ceiling, furniture, and, you guessed it, people. This creates this incredibly complex web of signals that all arrive from different paths. Engineers call it a multipath pattern. Now, see the person moving through that field of signals? Your body, which is mostly water, is really good at reflecting and absorbing radio waves. So as you move, you change the timing, the strength, and the phase of multiple signal paths all at once, creating this unique ripple, this disturbance in the pattern that a sensitive receiver can actually pick up and analyze. And that's the whole magic trick right there. Just think of the air in any room as being filled with this invisible, complicated web of radio waves. And any movement you make, no matter how small, standing up, opening a door, it subtly changes that web. I mean, in lab settings, researchers have used this to detect the tiny movements of a person's chest just from them breathing. If you have sensitive enough gear and some smart machine learning, you can analyze those tiny signal changes and figure out what caused them. And again, this isn't a security flaw, it's not a hack, it's just physics. How radio waves interact with the physical world. Which brings us to the big one, 5G's sensing superpowers. Okay, if Wi-Fi can already do this stuff in a lab, then what's the big deal about 5G? Why is it a potential game changer?
Well, this slide breaks it down perfectly. Compared to your Wi-Fi router or an old 4G tower, a modern 5G base station is on a whole other level. Instead of just a couple of antennas, they have dozens, sometimes hundreds. That means they can get a much higher resolution picture of the radio environment. And they don't just blast the signal out in a wide cone anymore, they can form these super narrow, steerable beams. It's like going from a floodlight to a laser pointer for sensing.
They also use much wider bandwidths, which lets them spot smaller changes more precisely. And they have incredible control over the signal's phase, which helps pinpoint where reflections are coming from. Every single one of these upgrades makes 5G hardware, at least in theory, a way better sensor.
Let's quickly break down these key technologies. First, you have Massive MIMO. That stands for Multiple Input, Multiple Output. All it really means is using a giant array of tiny antennas that all work together. Now, its main job is to send more data to more people at the same time, but the side effect is that it gives the base station this amazingly high-res view of the space around it. Think of it like this. It's the difference between your eye and a fly's eye. A fly has a compound eye with thousands of little lenses, giving it this incredibly detailed picture. More antennas in Massive MIMO act like those extra lenses, letting the tower see where signal reflections are coming from with way more precision.
The second superpower is beamforming. This is the ability to use all those antennas to electronically steer a focused beam of radio energy right at your phone, instead of just wasting energy broadcasting it everywhere. For calls and data, this is awesome. Less interference, stronger signal. But for sensing, it's like having a movable, high-powered flashlight in a pitch-black room. You could, theoretically, sweep these narrow beams across a space, measure the reflections from each spot, and then stitch all that information together to build a really detailed, almost radar-like map of whatever's in there. Now, when you put all of this together, you get what researchers officially call JCAS, which stands for Joint Communication and Sensing. This is really important to know. This is not some fringe conspiracy theory. It's an active, well-funded area of research for the future of wireless. It's the official name for the idea that the exact same signal and the exact same hardware can do two jobs at once: the obvious job of communicating and a much less obvious job of sensing the world around it.
And now, for what might be the most important part of this whole explainer. Section 4, Possible versus Deployed. This is our critical reality check. This is where we take all the mind-blowing potential of the technology and ground it back in the reality of today's live networks.
So, if the tech is so powerful in theory, why aren't cell companies secretly tracking people with it? Well, this slide lists the very real, very practical reasons why not. First, and this is a huge one, access to the raw radio data you would need to do this is locked down tight in commercial gear. The operator just can't get to it. Second, these base stations don't just run any old software. They follow super strict standardized profiles from a global body called 3GPP. And guess what? People sensing is not in the 5G standard. Third, this isn't some switch you can just flip on. It would take an insane amount of dedicated processing power and constant complicated calibration for every single cell site. It would also cost a fortune to run and, maybe most importantly, it would crash into a giant wall of legal, privacy, and regulatory problems. These are not small issues. They are fundamental roadblocks.
So this lets us shift gears and talk about what we should actually be thinking about. Section 5, the real risk, software. It's time to move past this idea of a hidden radar network.
You see, the biggest change 5G brought to the table wasn't just more antennas. It's a deep architectural shift in how networks are built. We are moving away from the old days where every network function was burned into a piece of fixed, single-purpose hardware. Now, we're moving to an era where those same functions are just defined by flexible, updatable software running on more generic cloud-based servers. It's the move to what we call a software-defined network.
And that creates a really interesting security paradox, which this slide lays out perfectly. Look, on our phones, at the user level, things get more secure every single year. We have stronger encryption, better identity protection, but at the infrastructure level, this new flexibility brings classic IT problems. More software means more places for bugs to hide. More complexity means a higher chance for human error, for someone to misconfigure something. And it's this exact flexibility that could allow for these dual-use capabilities to emerge. A feature designed to optimize a beam for a better phone call could, in theory, with the right software changes, be repurposed to analyze signal reflections in a way it was never meant to. That is the subtle, long-term risk.
So if the risk isn't some secret 5G feature today, where is all this actually going? That brings us to our last section, sensing in a 6G world.
Okay, this is the real takeaway for understanding the future. If you go and read the research papers and the industry white papers about 6G, that's the next generation of wireless that's on the drawing board right now, you'll see that RF sensing isn't some secret side effect. It's an explicitly listed foundational feature. It's being designed into the standard from day one. The conversation has totally shifted from could we do this to how should we do this? And what are the proposed uses? Well, for the most part, they're actually pretty beneficial. We're talking about things like super precise indoor location tracking for robots in a factory, way better than GPS.
They're imagining smart homes that can automatically adjust the lights and the heat based on where people are in a room to save energy. They're even proposing emergency detection systems, maybe for an elderly person's home, that could detect if they fall without them needing to wear any kind of device. These are the positive applications being planned. But of course, the same tech that detects a fall could also just detect presence, which is why we need to be talking about the rules now.
And that leads us to this quote, which I think just reframes the entire issue perfectly. 5G is the transition phase. 6G is where this conversation really belongs. Just think about that for a second. 5G built the flexible, software-based foundation and the advanced antenna hardware. It laid all the groundwork. 6G is where the applications, including sensing as a core service, are actually planned to be built right on top of that foundation.
So we'll end with this final thought. Look, the real concern isn't that some 5G tower is secretly watching you walk down the street today. The practical evidence for that just isn't there. The real long-term question that we as a society need to start talking about right now is this. As our physical environment itself becomes a massive distributed sensor network, what are the new rules we're going to need for privacy, for consent, and for security? The technology is being built out in the open. The policy and the ethics have to be built right alongside it. That's the conversation worth having. Thanks for tuning in.